Welcome to my video on axiomatic probability. First of all, what is an axiom? An axiom is a basic rule or assumption accepted without proof. Axioms are the foundation of mathematics. They're used all over. It's an assumption that defines things. In probability, we use axioms to define how probabilities behave. So why is experimental and theoretical probability not enough? We've got a prior video of mine. I went over experimental and theoretical probability. I've got a link to that video in the back of this one. In experimental probability, it depends on the data and may change with more trials. So it's not a set thing or an item. It can change. And that's not good in mathematics. You have to take that into account. And theoretical probability only works when the outcomes are equally likely. For example, rolling a fair die works. All outcomes are equally likely. But you get a 1, 2, 3, 4, 5, 6. Each have an equal probability. But what if the die is weighted and a 3 and a 4 come up a lot more than a 1 and a 2? So that would not allow theoretical probability to work. So it neither provides a complete mathematical foundation. This has been known for a long time. So in 1933, Andrey Kolmogorov, a Russian mathematician, introduced the axiomatic approach. It uses set theory. It provides a rigorous and universal framework for probability and used in all areas of modern probability and statistics. So first of all, let's define the probability space. The sample space is the set of all possible outcomes. In the case of rolling a fair die, it's 1, 2, 3, 4, 5, 6. And events are subsets of a sample space. Like, say you want a subset would be the numbers 1, 2, and 3. 1, 2, 3, 4, 5, 6. So that would be a subset or an event that you're looking for. The probability function P assigns numbers to events associated with these axioms. I'm going to give the axioms next. So these are the three axioms of probability. One is non-negativity. The probability of an event is always greater than or equal to 0 for any event. It's not a negative number. And the probability of the entire sample space is equal to 1, meaning in the case of a fair die, 1, 2, 3, 4, 5, 6, those are your only possible outcomes. If you take the probability of all of those, it's got to be equal to 1. And the additive property, if A and B are disjoint, that means they're mutually exclusive. They can't happen together. The probability of A union B is equal to the probability of A plus the probability of B. So disjoint events or mutually exclusive events cannot occur together. So their intersection is 0. See this Venn diagram? A and B are two separate events, and they don't intersect. It's just like heads or tails, or 1 and a 2 in the case of a die. So what are the consequences of these axioms? First is the complement rule. The probability of A complement, which we give a little C subscript there, is equal to 1 minus the probability of A. In the case of a coin toss, you either get a head or a tail, so the probability is 0.5 of each event. So 1 minus 0.5 is equal to the probability of a head or a tail. If you start with a head, then you're going to get a tail. The probability of an impossible event, or the null set, is equal to 0, meaning if you're not looking at anything in the space, probability space, has got to be 0. And the general additive rule is expanding it slightly, is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of whatever's in the intersection here. Because basically what you're doing is you don't want to double count. You added A and B together, but now you have to subtract off their intersection so that you don't count these elements in A intersection B twice. So that's what that means. And then the probability, just like in theoretical and experimental probability, it's got to lie between 0 and 1. So it's very similar to the other theoretical and experimental probability we talked about earlier, but this is a more rigorous mathematical definition. Let's take the example of a simple coin toss. The sample space is heads or tail. Those are your two possible events. Probability of a head is 0.5. Probability of a tail is 0.5. So let's check these axioms to see if they're validated here. So non-negativity, both the probabilities are greater than 0, 0.5 and 0.5. Normalization property, probability of a head plus the probability of a tail is equal to 1. Okay, 0.5 plus 0.5 is equal to 1. Now, the additive, so if the probability of a head and a tail are disjoint, meaning you can't have, they're mutually exclusive, they can't occur together. You can't get a head and a tail in the same coin flip. So the probability of a head union tail is equal to 1. In a coin toss, heads and tails are mutually exclusive. Since they cover the entire sample space, the probability of head union tail is 1, representing a certainty. So why are we working with these axiomatic probabilities? Why do they matter? It works beyond the simple counting cases. It works in more complex examples and a lot more. It gives us the whole range of items that we can look at. Handles continuous probabilities, in the case that we're not just counting finite integers, and it works during intervals and provides a consistent foundation for all probability models, and modern probability theory is built on these axioms. Well, I hope you got something out of this video on axiomatic probabilities, learned a little bit about it. If you did, give me a like, thumbs up, subscribe to my channel. I want to thank you for watching.